So in this video, what I want to do is try to make a sort of qualitative connection between the idea of flux that we've already talked about in the one-dimensional case and the idea of surface integrals and also integrals along one-dimensional surfaces that are not straight lines. So you remember the idea of flux that we've already sort of dealt with is this sort of concept of asking the question how much stuff is passing through a given surface per unit time, right? So you've got some sort of flow of physical material or some flow of energy or whatever it is, and that you're asking the question how much of that material is actually passing through a given surface. And we thought about that first in just the sort of simple case of a pipe, right? So we sort of thought about taking some surface that was a cross-section of the pipe and sort of sitting at this point, this is an eyeball watching, and asking the question how much stuff is passing through that surface per unit time. Now, at the end of the last set of studio problems, there were a couple of questions that were trying to generalize that idea of flux. Let me draw a sort of couple of pictures to get at that. The first one is this question that had to do with a river, right? So there's some river here, and I'll sort of attempt to draw this in a way that kind of makes some sense, right? So this is sort of the cross-section of the river. Maybe that cross-section is changing, and as you go along, maybe there's sort of a deep hole here, and maybe it gets shallower over here, right? You know, whatever. But you've got this sort of general idea that this is a river, if you can possibly interpret my really bad picture, right? And I've sort of drawn an edge here, but that just means I've got water that's coming in here and water that's going out over here, right? And so through the course of this river, the water is sort of flowing in different directions. Maybe there's a little whirlpool over here, right? Various things happening in this river at different depths and at different positions. And you could imagine inserting into this river a sort of gill net, right? So let's say I've got a net that I stick into the river, right? And maybe here's the frame of the net, but the net actually might be some, surface in the river, which is not necessarily flat, right? It might be sort of a messy looking thing like this. So there's my net in the river. And I asked the question, how much flux is there through that surface? Now, you can think first about formulating this using the sort of notation that we've already developed, right? You're going to be integrating over that surface, right? So it'll be a double integral over that surface. And there'll be some sort of differential area that we're dealing with. But then we need to ask the question, well, what is this thing that we're adding up? And what we're really adding up is sort of how much stuff per unit area is flowing through each of these little chunks, right? So if I sort of take this and I blow it up, so I've got this gill net, right? I've got some little area dA here, right? This is my differential area. And I'm asking the question, what's the flux through that bit of area? What's the flux through this bit of area? And I'm adding all that up, right? So this is the sort of flux per unit area at that point on the surface, conceptually speaking. Right? So that's sort of what we mean conceptually when we talk about calculating flux for some arbitrary surface, is we're actually integrating over the surface. I'll note that you can do that in a sort of smaller number of dimensions as well. For example, the second question on the studio problems has to do with the town of Needham, right? So here's Needham, there's Great Plain Ave, and here's Harvey's, and over here is Olin, and there's the center of town, and the town green is here. Mark's house is someplace over here. I won't tell you exactly where because that'd be kind of creepy. But the question was, how do you figure out what the number of cars leaving Needham per unit time are, right? And if you think about that, what you need to do is define a boundary, right? And in this case, the boundary is not a surface. It's actually basically a one-dimensional object embedded in this two-dimensional space. It's a line. It's a contour that defines the edge of the town. And then what you do is you ask the question, well, as I move around that boundary at different points along that boundary, there might be some cars coming in, there might be some cars going out. So what I'm going to do is integrate around that contour, right? So if I call that contour C, and I need to ask the question, how many cars per unit length per unit time are passing across that boundary times the differential length on that boundary, right? So I'm going around this surface, and at each point I'm asking how many cars are passing through this DL, how many cars are passing through this DL, and so on. Right? So whether I'm talking about a sort of two-dimensional surface embedded in a three-dimensional system, or a sort of one-dimensional surface, a line that's embedded within a two-dimensional space, in both cases it sort of makes sense to talk about flux by basically adding up something that you might think of as being sort of a flux density along that contour. So that's just conceptually what we mean when we talk about figuring out flux. So there's some mathematics we need to introduce in order to get much further with it. But let me just say one thing about the way that we often think about defining flux. And it really has to do more with this picture than with the former picture. You'll notice in this picture, this is a closed contour, right? It's actually enclosing the town. And so you're actually asking a question, how many cars net are leaving the town, are going out of this entire surface? And in order to do that, in order to ask that, you need to come up with a sign convention that has to do with whether you're talking about this being inside or this being out inside, right? So we want to define flux with regard to when you've got a closed surface, the flux is positive when your total flux is greater than 0. So if I say here that my total flux is the integral around this contour of the amount of stuff coming out, it's the amount of stuff coming out that gives me positive terms. I also want to say, just notationally, you'll often see something that looks like this on the integral, which is saying the integral around a closed, in this case, since it's a one-dimensional object embedded in two-dimensional space, closed contour. If it were a sort of surface that was closed, right, if we were interested in a flux coming out of a balloon, you would have the closed contour of the integral over that closed surface, and you'd be integrating over that area.